Welcome to the workshop. Today we want to take a look at section 3.1, random variables. And in this section, we're going to introduce a little bit of notation, of course, define what a random variable is, and just kind of introduce ourselves to the context so that way we can use the idea of a random variable throughout this chapter. So let's take a look at our notes. A random variable, if you think back to maybe an elementary statistics course, they may describe it in a number of different ways. My preference is to describe it as it is a variable whose value depends on chance or is assigned randomly, usually found through randomly selecting an object. Okay. So that kind of makes sense. It's an intuitive description of a random variable. But in our axiomatic buildup of probability and more formal definitions, we have a much better definition of a random variable. So interestingly enough, despite being called a random variable is actually a function. Okay, so if S is a sample space with probability measure X, so we have a probability measure on it. That's what we talked about in chapter 2. And X is a real valued function, right? X is a real valued function defined over the elements of S. We have those two conditions. We have a probability measure and we have a real valued function defined on the elements of S. Then that function is in fact a random variable. So a random variable is actually a function. Interesting. Random variables will always be denoted by capital letters, and the values that a random variable can take on will be denoted by a lowercase letter. So if X is the random variable, then lowercase x would be the possible values that the random variable can take on. So we'll see that here in our first example. So in our first example, we're going to try and not really consider a context. In our second example, we will. But here, I want to try and focus a little bit more on the idea that X is a function. It doesn't have to have a particular meaning. That's not a requirement in the definition of a random variable. So let's take a look at an example where the meaning doesn't really seem to be there. So the elements of our sample space, the possible outcomes, are Tommy, Heath, Jim, Keller, Two-Tone, Alex, and Jenny. Those are the elements of our sample space. There's 1, 2, 3, 4, 5, 6, 7 elements in our sample space. Okay, so if I take the function x and I plug in Tommy, I want to have a real number output, and that number is 8. Okay, so x represents the value that the function x takes on. So lowercase s x gives the value of the random variable. All right. So I input Tommy, I get 8. I input Heath, I get 6. I input Jim, I get 7. Keller, 5. Two-Tone, 3. Alex, 0. And Jenny, 9. Okay, excellent. That's it. Now we also have the probability of each of these outcomes occurring in our experiment. What's the probability of us getting Tommy? 1/12. Heath, 2/12. Jim, 1/12, and so on. So we want to observe, of course, that this is in fact a probability measure. So we should have that the probability of anything is greater than 0, which is true. We should also have, well, greater than or equal to, and the probability of the sample space occurring is 1, 112 plus 2 12s plus 112 plus 2 12s plus 112 plus 2 12s plus 3 12s is in fact 12 12ths, which is 1. So yes, probability of the sample space is 1. And then each of these outcomes are distinct from one another. So if I want the probability of Heath or Jim, then it would be 2 12ths plus 1 12th, the sum of the individual probabilities. Excellent. So that's what we need to have a probability measure. So we've got a probability measure, we've got a value assigned to each outcome in the sample space. So what we have here is in fact a random variable. Okay, so we're going, in this case, x, right? The values of x are just given here, so no context. Excellent. So I'd like to investigate this just a little bit further. We already said that a probability measure is given, and there were essentially 3 conditions that we had to satisfy. The probability of each event is greater than 0. Well, yeah, the probability of each event occurring is greater than or equal to 0. We have that. The probability of A or B is equal to the probability of A plus the probability of B, because they are disjoint sets or mutually exclusive events. And then 3, the probability of the sample space occurring is actually 1, right? And this can be verified by the sum of 1/12. Well, probability of S is the sum of the probabilities of the individual outcomes. So 1/12 plus 2 12ths plus 1/12 plus 2 12ths plus 1/12 plus 2 12ths plus 3 12ths is in fact 12 12ths or 1. Excellent. So this, right, these are the postulates that needed to be satisfied for a probability. So this is a probability measure. We're good to go. Is x a real valued function? Yes, of course it is. It takes on several real values. Yes, it takes on real values only. Okay, right, those numbers, those real values are 8, 6, 7, 5, 3, 0, and 9. So we want to identify the domain. Well, the domain is simply the sample space, right? So that's Tommy, Heath, Jim, Keller, Two-Tone, Alex, and Jenny. Excellent. And then what's the range? Well, the range is exactly those numbers that the function takes on. 8, 6, 7, 5, 3, 0, and 9. Excellent. And then what we want to recognize is this notation. This represents an event. So when we say that x is equal to 9, we're actually giving an event. So some of you may be familiar with this already. I forget which course it lands in, but we should actually think of this as the event, right? So this refers to the collection of outcomes given by this set. Okay, so the inverse, if we have a function, we can take its inverse. Now, typically we say the inverse, right? I'm not saying inverse function here, I'm just saying inverse. And so this is a set, and it's the set of all inputs of x that give us 9 as an output. So this would simply be Jenny. That's the event that it represents. You don't need to know this notation, so I'm going to get rid of it. I'm going to get rid of it because it's not what you need to be familiar with. What you need to be familiar with is that this represents the event, and that event is the event of, the event of, it's the event containing all outcomes in the sample space for which x is in fact equal to 9, right? The random variable is equal to 9. Excellent. So in this case, we're just looking at Jenny. That's all that we have. That's the only input. That's the only outcome element of S. S is a sample space, so it's the outcome of the experiment. It's the only outcome for which the random variable is taking on the value 9. All right, so that's our introduction to random variables. We'll take a look at another example that has a little bit more of a context. Less references to good songs, more actual context. So I'll see you guys back in the workshop very shortly.